Hello everyone, am I audible? Hello,
Yes, sir, you're audible.
and the screen is also visible.
Yes, sir.
Okay, so let us start with what we have left in the last class. Uh, Let me just. So can you see the screen on this forced convection? Hello.
Yes, sir.
Okay. So before the minor one, we started looking at the forced convection. We started with the argument saying that in the forced convection, in order to solve the heat transfer problem, first we have to solve the momentum transfer problem, and then based on that, the velocity distribution has to be put into the energy balance, and then finally the energy balance has to be solved. So even though the modeling can be easily done, but solving the model computationally is difficult, isn't it? That is what we have argued. Based on that, then we said that instead of doing this, uh, what people have done is they have basically done the dimensional analysis and found that what are the different dimensionless numbers which are going to affect the heat transfer coefficient. So once we know that these are the dimensionless group which are important for a particular problem, then based on these dimensionless numbers, different correlations are formulated. Okay. So now these correlations are then formulated based on performing the experiments like the experiment in the double pipe heat exchanger, where all variation in the properties as well as diameter as well as velocity is done, and then based on that the correlations are formed. So this is one way of doing it. So different correlations we have seen, isn't it, in the last class? So then after that, what we have said that uh, though the correlations we know, isn't it? But there are some cases in which not only the change in the properties is also there, but also the temperature gradient also changes along the length. So in such cases, for example, in a double pipe heat exchanger, here you can see the temperature difference between the two streams changes as we move along the length of the pipe. And in such cases, we cannot apply directly the Newton's law of cooling, which says H is given as UA delta T, because this delta T itself is variable. So in such cases, delta T LMTD is used. So that also we have derived for the co-current flow, but for a counter current flow also we can derive the same expression, and that derivation is there in the book. So you can go and look at it. So this is what we have seen in the last class. Okay. Now what we are going to see today is, see, so far we were looking at, making the correlations based on the experimental thing, and then, finding the heat transfer coefficient, putting this heat transfer coefficient directly in the heat transfer problem and solving. Okay, that is what we have seen so far. Now, there are different, researchers have said that we can find out this heat transfer coefficient directly by performing the analogy with momentum transfer. Okay. So by performing the analogy with momentum transfer, uh, we can easily find out the heat transfer coefficient, and we don't require explicitly the correlations for the heat transfer coefficient, and we can roughly find out the values of the heat transfer coefficient if we know how my friction factor is varying. So if this knowledge is known, then we can find out how my heat transfer coefficient is going to be based on the analogy between momentum and heat transfer. Okay, so let us look at this particular part in little bit more detail, and then we will start with the free convection. Okay, so here in this particular slide, you can see for a laminar flow, we can write down the expression for the momentum transfer. Nothing but the velocity along the x direction. The distribution of the velocity is along the radial direction r. That is what we see in a circular pipe, isn't it? Uh, uh, so here you can see the shear stress can be represented as minus mu dux by dr. Again, we can rearrange this particular equation and we can write this equation in terms of kinematic viscosity. So we divide this equation by rho, so that becomes minus mu by rho d by dr, and the rho is multiplied here in the differential. So that becomes d by dr of rho u. So this equation can be then written as minus nu d by dr rho u, where nu is nothing but kinematic viscosity. Okay. Similar to this, we can write down the Fourier's law of heat conduction. So that can be written as heat flux is given as minus k dt by dr. So we are not having any minus sign here because we are assuming that the temperature of the wall is higher than the temperature of the fluid which is flowing inside this pipe. So that means as the R is increasing, the temperature is increasing, and therefore this negative sign is omitted here. So Q is given as Q is given as k dt by dr. Again, we can rearrange this equation. So we can rearrange this by dividing by rho Cp. So that becomes k by rho Cp d by Cpt. So this can be given in terms of the thermal diffusivity, and that is alpha d by dr rho Cpt. Okay. So this is for the laminar flow. Now, similar equations can be written for the case when we are looking at the turbulent flow. So for a turbulent flow, in addition to the usual this kinematic viscosity or a thermal diffusivity, we also have an additional factor which is corresponding to all the eddies or the turbulence which is being created because of the flow. So that is accounted through another two parameters which are nothing but momentum diffusivity, which is nothing but epsilon m, and the thermal diffusivity, which is nothing but epsilon h. So both these equations which we have seen for the laminar flow can be written for a turbulent flow with these two additional parameters. So tau, which is nothing but the shear stress, is given as minus in the bracket nu plus epsilon m d by dr rho u, where epsilon m is nothing but the momentum diffusivity. And similarly, for a heat transfer, we can write down heat flux Q as alpha plus epsilon h d by dr rho Cpt. Okay. So these are equation number 1 and 2. Now, again, from these two equations, we are finding out what will be the wall shear stress. So wall shear stress is nothing but the shear stress at the wall. So we can find out directly from equation number 1 by putting R equals to capital R, where capital R is nothing but the radius of this pipe. So we are looking at the wall shear stress exactly at this surface of the wall here. So we can write down that as TW, that is nothing, tau W, that is nothing but wall shear stress. So tau W is given as minus V plus epsilon m d rho u by dr, and that is calculated at R equals to R. And wall shear stress is given by in terms of fanning friction factor. So the frictional head here is given, that is half f rho v square. So that is nothing but the frictional head, and where f is nothing but fanning friction factor. Okay. So this we can directly write in terms of the friction factor. So wall shear stress we can write in terms of the frictional factor, and the frictional head in this case will be given as half f rho v square, where v is nothing but the mean fluid velocity. Okay. So again, this particular equation we can rearrange and we can find out the dimensionless velocity gradient, where dimensionless velocity gradient is nothing but u by v, that is nothing but dimensional velocity, and gradient across the radius. So that is du bar by dr, where u bar is nothing but u by v. So that is calculated as that. If you rearrange this equation, what you get is fv divided by 2 nu plus epsilon m. That is what you are going to get. So dimensionless velocity gradient at R equals to R we can represent in terms of the fanning friction factor and the kinematic viscosity and eddy, the momentum diffusivity. So that is given by equation number 3. A similar equation we can write down again for a heat transfer problem. So in a heat transfer problem similar to the momentum transfer problem, we are finding out the dimensionless temperature gradient. So dimensionless temperature gradient is found out here in the equation. So let us look at the equation number 2. So this equation number 2 is first written for the heat flux at the wall. So heat flux at the wall is given as, wall heat flux is given as QW. So that is again given by alpha plus epsilon h d rho cpt by dr at r equals to r. And as you can see, the wall heat flux here can be given as in terms of the Newton's law of cooling. So that is h delta t. So that is what is written, h tw minus tm, isn't it? Where Tm is nothing but the mean fluid temperature and Tw is nothing but the wall temperature. H is the heat transfer coefficient, inside heat transfer coefficient. So now this equation of wall heat flux is rearranged in the form of, uh, dimensionless temperature gradient. So dimensionless temperature gradient here is given as dt bar by dr at r equals to r. So that is dimensionless temperature gradient at the wall is calculated, where t bar is nothing but t by tw minus tm. So this tw minus tm is divided to this t to define t bar. Okay, so dt bar by dr at r equals to r is given as h divided by rho cp in rho cp alpha plus epsilon s. So this is the equation number 4. So are you all able to get it? What we are doing? Hello? Hello? Am I audible to everyone?
Yes, sir.
Yes, sir.
So are you all able to get it? What we are doing?
Yes, sir.
Okay. So what we have done is we have started with the laminar flow. Then we have looked at the momentum transfer, we have looked at the heat transfer. These two equations then we have extended for the turbulent flow by adding this momentum diffusivity and eddy diffusivity. And then these two equations we have written at the wall here when r equals to capital R. And also in addition to that, what we have done is we have found out what will be the we have found out the wall shear stress and wall heat flux, and based on that then we have found out the dimensionless velocity gradient at the wall and dimensionless temperature gradient at the wall. These two quantities we have found out in equation number 3 and 4. Okay, now what is been given by Reynolds? What Reynolds said is, while making the analogy, what Reynolds said is the gradient of dimensionless velocity and the dimensionless temperature at the wall is equal. That is what the uh, Reynolds has given. This is what the Reynolds has assumed. What he said is the dimensional velocity gradient is same as dimensional temperature gradient at the wall. Again, the another thing which Reynolds assumed is the summation, this kinematic viscosity with plus momentum diffusivity is same as thermal diffusivity plus the uh, thermal diffusivity plus eddy thermal diffusivity. Both these are the summation of the as kinematic viscosity plus eddy momentum diffusivity. Okay, so that is given by equation number 5. So these gradients are first equated. So gradients we have already found out from equation number 3 and 4. So these are equated here. So these are equated here. So equation 6 is directly coming by equating the dimensional velocity gradient and dimensionless temperature gradient. Now again, in addition to that, from equation number 5, nu plus epsilon m is same as alpha plus epsilon s. So this also get cancelled out. So finally what we get by rearranging this entire thing is we get Nusselt number divided by Prandtl number and Reynolds number. So that comes out to be a Stanton number, and Stanton number is represented as F by 2, where F is a friction factor. Okay. So this is a very, very important result. So why this result is very important? Because now just by looking at the Reynolds number versus friction factor chart, which is nothing but Moody's friction factor chart, we can find out what is the friction factor corresponding to a particular Reynolds number. We can just put it in this equation, Stanton number, which is defined as Nusselt number divided by Prandtl number and Reynolds number, and Nusselt number is given in the form of HD by K. We can directly find out the heat transfer coefficient. So this equation gives me a relation between a friction factor and heat transfer coefficient directly. That's a very important result. So you don't have to make any correlations. You find out the friction factor, and if you know the friction factor, you can find out the heat transfer coefficient. So can you see the advantage of these analogies? Isn't it? We started with saying that this problem is difficult, isn't it? We started with that argument that this problem is difficult because both velocity problem as well as the heat transfer problem has to be solved simultaneously. Then we said that we will simplify this by using the correlations, isn't it? And now we are saying that we don't require even correlations. We are saying now that we don't even require a correlations. We just require a friction factor. If you know the friction factor value by some means, then we can just find out the heat transfer coefficient directly. That is what it is. Okay. Now there are some disadvantages with this particular analogy. The disadvantages is what we have assumed in this case is, you can see we have started with equation 1 and 2, even though we started with laminar flow, but actually we have worked on the equations of the turbulent flow. These laminar flow equations we have only used for deriving this 1 and 2. That's it. But essentially what we have assumed that the entire flow in this cross section of the pipe is turbulent, but that is not the case, isn't it? So the fluid layer which is very close to this pipe is going to be stagnant, and that is a layer nearby to that is going to be a laminar in, isn't it? You are going to have a laminar flow there. So you are going to have a laminar sublayer, even though you are having a turbulent flow through the pipe, isn't it? So we are not representing a complete picture. We are not representing a complete picture. So a more refined equation is given by Prandtl. What Prandtl assumed is eddy transport in the turbulent core. So that means between this region here, there will be a eddy transport, but very close to the wall, there will be a laminar flow. So both these factors he accounted, and the diffusive transport in the laminar sublayer. So both these factors he accounted, and based on that he has given another equation which is nothing but a Stanton number, which is defined as Nusselt number divided by Prandtl number into Reynolds number, and that is again given in the form of friction factor, but slightly more complicated equation. But still this equation is also in the form of friction factor only. So the Stanton number is given by F by 2 divided by 1 plus 5 under root F by 2 into Prandtl number minus 1. Okay. So this is a more refined equation given by Prandtl. That is why it is been written. It is more realistic. There are some more correlations given by the other people based on the experimental data. What they have found that instead of having a Stanton number where only the Prandtl number is multiplied here, instead of that the Prandtl number will be having 1 by 3, power 1 by 3, and therefore the Nusselt number divided by Reynolds number into Prandtl number raised to the power 1 by 3 is given as by 2. That is given by Chilton and Colburn. And the question they have the friction 0.04 0.2. And if you write this equation directly in the form of JH factor, so JH factor is nothing but F by 2. So you can directly put it, this Nusselt number divided by Reynolds number into Prandtl number 1 by 3 equals to JH. Then JH is given as 0.023 Reynolds number raised to the power minus 0.2. Okay, so these are the correlations given by Reynolds, Prandtl, Chilton and Colburn. Advantage of these correlations are now you are enabled to find out the heat transfer coefficient even without looking at the correlations. You can directly find out the heat transfer coefficient if you know the friction factor. So if you know the momentum transfer problem well, then you can solve the heat transfer problem directly without any complications. That is what it is. So are you all able to get it? Hello?
Yes, sir.
Is it clear to everyone?
Yes, sir.
Yes, sir.
Okay, so let us move to our next chapter with this convection. This I have already uploaded on Moodle. So let me just start the next chapter, which is nothing but okay. So these new slides are visible to everyone. Hello. Hello. So the slides of free convections are visible to everyone.
Yes, sir. Now they're visible.
Okay. Okay. So far what we were looking at the forced convection where uh, the flow of the liquid was caused by the external force or the external uh, pressure difference. Okay, now in this case in the free convection what we are seeing is the motion in the fluid is caused by the density difference during the heating or the cooling of the fluid. So no external medium is used for inducing a flow or a motion in the fluid. Okay, so let us look at some of the uh, salient features here. So free convection or a natural convection pertains to the motion of the fluid caused by density differences during heating or cooling of the fluid. A common example is if you heat a liquid in the beaker in a laboratory, isn't it? So you are heating it from the bottom. So what will happen is the fluid which is very close to the bottom surface is going to get heated, and because of that the density of this liquid which is very close to the bottom is going to decrease. Compared to that, the fluid elements which are present at the top layer are going to be at lower temperature and therefore will have a higher density. And what will eventually will happen is since the density of the fluid elements which are there at the bottom is going to be low, these fluid particles are going to move up because of the density difference, and this is going to cause a motion of the fluid elements in the beaker. Okay, so this is going to cause the convection currents. So that is what is been written here. So the buoyancy force comes into the play in such type of things. Uh, the phenomena is called as free convection or a natural convection because no mechanical device or external uh, force is imposed here to create a motion in the fluid. Again, there are numerous examples of the free convection. This is very important in the industrial operations because there are numerous industrial operations where the material is heated or cooled, and in order to minimize the heat loss, these are surrounded by the insulation material. But very often you will see that the temperature of this insulation material at the surface of the insulation material, insulation surface is generally is at a higher temperature than the ambient temperature, and because of that there is a free convection taking place from the insulation surface to the ambient. Okay, so this is commonly seen when the steam pipes or the reactor vessels or furnaces are surrounded by a the insulating materials. Okay, so even though the insulating material is there, but the temperature of the surface of the insulating material is going to be higher than the ambient temperature, and therefore the heat loss takes place by a free convection. So these are the common example. Okay, so let us look at some more details of uh, the free convection. So consider a vertical wall. When a plate is heated, a free convection boundary layer is formed. The velocity profile in the boundary layer is quite unlike the velocity profile in the forced convection boundary layer. Let me just explain things in a little bit more detail. Okay. So in fact, let me just draw one more figure here.
Excuse me, sir.
Yes, please go ahead.
Sir, your voice gets lagged sometimes in between.
Okay.
And it's happening quite frequently.
Probably that is because the internet connection is not good. Am I audible now?
Sir, you're audible, but it gets lagged sometimes in between.
So that is all because of the internet connection here at IIT. So let's hope that it will get resolved. Uh, because is it now, or am I audible now?
Yes, sir.
Is it lagged now?
No, sir.
Okay, so let us continue. You stop me in between if some lag is coming, or if my voice is not audible to anyone. Is it audible to others?
It is now, yes, sir.
Is it
Yes, sir.
audible to others, or this problem is only with one student?
No, sir, it is lagging, but it right now it is okay.
Okay, so that means it's the problem at my end. That is what you are trying to say. Correct? Okay. Okay, stop me in between if it's not audible. Okay. Okay. So let me just draw one more figure here that will give you a little bit. Let me change the color. Let me change the color a little bit so that you will understand. Okay. Again, let me just draw one more line so that it will be clear what. So what I am trying to say here is uh, I have drawn two different profiles here. The first profile which is given in the red, the boundary layer profile which is given in the red, is for the velocity profile, momentum boundary layer, whereas the boundary layer which I have given in a blue colored font is a boundary layer corresponding to uh, the temperature, that is a thermal boundary layer, that is a thermal boundary layer. Okay, so here you can see, now you can clearly see the difference here. So this wall, this vertical wall is at a higher temperature, let's say TW, and since we are looking at a free convection, that means this fluid is initially at a stagnant mode, so this fluid is not moving. This temperature of the wall is higher than the free stream temperature T infinity. So TW is greater than T infinity. So what is going to happen is over the period, the fluid elements which are very close to this wall are going to get heated, uh, and we are going to have a thermal boundary layer like this. And because of this temperature difference, there will be a change in the density of the fluid element, and that is going to cause the motion of the fluid in a upward direction. So the velocity profile of the fluid element will look like as shown here by U. Okay, so the velocity of the fluid element very close to the wall is going to be zero, even though the temperature is very high, but because of no slip condition, the velocity here is going to be zero. And the velocity of the fluid at the free stream velocity here is going to be zero, because here the temperature is very low. Because of that, there will not be any movement of the fluid element up. Okay, so a typical velocity profile which we are going to look at is something like this, which is shown here. So this is unlike to the velocity profile we have seen uh, in a forced convection regime. I can go back and show you the velocity profile which we have seen in the forced convection regime is quite different. Maybe I just open that file and